Okay, we are back in better than ever. We're going to wrap up the standard normal distribution discussion. And just a little bit of a hint or help here when you're doing this. If a random variable has not been standardized, you need to go ahead and standardize it. Then once you've done that, sketch a standard normal curve and shade the required region. Then you'll be sure you know what it is that you're looking for, and you'll be able to figure out whether or not you need to subtract it from 1. And then use the tables or the graphics calculator to find the probability. Okay, so given that x is a normal variable with mean 62 and standard deviation 7, find without using technology these probabilities. Well, this is not a standard normal variable because it doesn't say it. It doesn't say z. The mean is not 0 and the standard deviation is not 1. So we know that we need to standardize it. So I'm going to do that for part A here. Z, using your formula sheet, to standardize a variable, a random variable, would be 69, the data itself, minus the mean, 62, over the standard deviation. So z would be equal to 1. Okay? So the probability that x is less than or equal to 69 is equivalent to the probability that 69 standardized for this set of data, z, is less than or equal to 1. Okay? And that's very straightforward if you remember that the table gives you the area to the left of the curve. So that means that that probability is approximately equal to, whoops, sorry about that, approximately equal to, we go to 1.0, here we go, 0.841, or about an 84.1% chance of that occurring. Okay. Part B, okay, we're going to have to standardize each of those. So Z, I'll call Z1 for 58.5 minus 62 over 7, and I will tell you that's equal to negative 0.5. And then Z sub 2 is equal to 71.8 minus 62 over 7, which is equal to, I think, 1.4. Is that it? Yes, 1.4. Okay, so now this changes to the probability, instead of this, that negative 0.5 is less than or equal to z is less than or equal to 1.4, which means we can use our handy dandy table now. Fantastic. Okay, so what does the sketch look like? So we know what we're doing. We can think about what we're doing. What's our strategy? Remember, our table gives the area to the left of the curve. So I'm going to take the probability that z is less than 1.4. So that's all of this, everything to the left of 0.4, minus the probability, minus this area right here that's less than negative 0.5. And remember what we have to do with the negative. We'll get to that in a second. Okay, so now the probability that z is less than or equal to 1.4 minus the probability that z is less than or equal to negative 0.5. And remember what we do for the negative? So this equals, this is the same thing, the probability that z is less than or equal to 1.4 minus, remember when it's negative, we have to do 1 minus the probability that z is less than or equal to the positive value of that, 0.5, because of symmetry. And from our chart, 1.4, let's see, so that's going to be 0.9192 minus 1 minus the probability that z is less than or equal to 0.5. So 0.5, 0.6915, 0.6915. and that comes out to be approximately equal to 0.611. So that means there's a 61.1% chance that the data will lie between negative 0.5 and 1.4, or back to the original question, 58.5 and 71.8. And we're able to do that because we standardized it. Okay, that brings us to quantiles, or k-values. Basically, all that k-values are is, instead of finding the probability, like, well, let's go back to this first one. Instead of finding the actual probability here, we're given the probability and we're asked to find either the standard normal variable or just the normal variable. Okay, and there is a table for that we will use. It's called the inverse normal probabilities table. Okay, and there's a lot more to it than this. This is 2 pages long, but I just cut out the piece that we need from our formula sheet. Okay, so what the heck is going on? So we're finding k for which p is less than or equal to k is equal to 0.95. Given that the normal or the random variable x is normally distributed with a mean of 70 and a standard deviation of 10. Remember, 10 squared is the variation, so that means 10 is the standard deviation. And x is measured in millimeters. Okay, so what is really being asked for here? Okay, we're saying, first we're saying, what is the probability that x is less than or equal to k, that probability is equal to 0.95. For what value of k is this true? So what we're really asking is, for what value of k is this true? That the random variable x, well, no, let's do it this way. That the z-score, this is a little bit easier to understand, is less than or equal to, I'm going to have to standardize this variable because it's not standardized right now, is equal to k minus the mean of the data over the standard deviation. For what value of k is the probability 0.95, or 95%? So really what we're asking, if I go to the standardized table here, 0.95, okay, the standardized probability is 1.6449. So what it turns out to be is, for what value of k is the probability equal to 1.6449. Okay. Well, why did I go from this to this? Because this probability for a standard, or for a normal distribution, corresponds to this probability for for this area for a standardized normal probability. So we are looking for that value of k. Okay, and that would be k. If you solve that algebraically, that's approximately equal to 86.4. Okay, what does that mean? That means that approximately 95% of the values are expected to be 86.4 millimeters or less. Okay. On the calculator, that's very simple to do. Let's go do that real quick. We would go to, let's get the calculator up. We're going to our inverse norm this time. So let's see, probability, distributions, inverse normal. Okay, and the area that we want is 0.95. Okay, let's see, the mean is 70. And then the, what is standard deviation? 10. We hit OK. And we get 86.4. So if we have a calculator, it's a lot easier. We don't have to mess around with the conversion or anything. We just plug it right in there. Okay. That is it. One more video and we are done. See ya!